Welcome to Module 1 for Experiment 1, which is going to deal with chromatography. Chromatography in general is going to refer to the separation of molecules based on their preferential distribution between two different phases. We're going to discuss in thorough what those phases are and how the separation works. Before we do that, why chromatography is important to us is it allows us to separate the components of mixtures, to determine how pure a sample is based on how many spots we see from separation, to identify unknowns by matching them to reference spots for possible known compounds, and to monitor reactions. So if I have a starting material, I can track its conversion to product based on the number and types of spots I see on my TLC plate. So shown here in fluorescent green is a typical TLC plate like the kind you're going to get in lab this week. We'll talk about how this visualization works and how we can think about the location that these spots appear and learn different things about our molecules. So by the end of this module, and largely by the end of experiment 1, we hope that you can define the phases required for chromatography. And our case is going to be a mobile phase and a stationary phase for both our TLC and our column chromatography in experiment 1. We're also going to look at how we can describe where a spot shows up on the plate. This is known as an RF. And we're going to be able to look at the structure of molecules and determine what we might expect for their relative positions on a TLC plate, and how what is known as the mobile phase identity can change the position of that RF. So might sound like a lot of new information up front, but by the end of our discussion, you should have a good idea of how to think through these concepts. So let's start by taking a look at the components of a TLC system. Okay, so in order to produce the type of plate that was shown on my opening slide, what we have to have is a stationary phase, a mobile phase, and a developing chamber. Okay, so in week 1, the developing chamber will be this 250 ml beaker placed in your hood, okay? And we typically cover this with tinfoil or watch glass to keep all of the solvent vapors from our mobile phase saturated within the chamber, okay? So let's start by talking about the mobile phase. The mobile phase is going to be a solvent placed at the bottom of your jar. Okay, and we'll look at the particular organic solvents most commonly used as a mobile phase. Shouldn't surprise you that this is the mobile component. When you think of a liquid, we associate the properties of a liquid with the ability to move. Okay. Lastly, we're going to use a TLC plate coated with a white powder known as silica gel. This coating, shown here along the surface, is known as a stationary phase because it will not move the way the liquid will move up the plate from the bottom of the chamber throughout our chromatography process. So these are the bones of your chromatography setup. Before we talk about how this separation works, let's work through logistics of how you're going to start with solutions of molecules you're interested in the lab and get them into your TLC chamber. So you're going to start by receiving a TLC plate from your instructor, and that TLC plate is coated with silica gel white powder on the surface. The powder is coated on really fine, and it's somewhat sensitive. So what you want to do is not handle the plate by grabbing it from the center. Instead, you want to touch it along its edges, and you want to try to use clean gloves so that you don't contaminate the surface of the plate. Okay. What you're going to start by doing is using the pencil from your personal tote to draw a very thin, fine line along the base of the TLC plate. This will allow you to have a starting point where you will spot your solutions of your compounds. We call this starting point a baseline. Okay. So this is how we keep track of where we put our material onto the plate. You'll notice we don't put it at the very bottom. We leave a little bit of room, and we'll talk about why that is. Very gently with your pencil markings, you can label individual lanes where you will be placing a drop of your solution. So for instance, in lab this week, you might have a lane for caffeine standard, and a lane for acetaminophen, and a lane for a mixture. Okay. So you can mark those off with some kind of code that you will remember. And then what you're going to do is you're going to be given a solution of each of these components. Okay. Well, how do you get the solution onto the plate? Okay, you only want to place a small dot of that solution right in the desired lane. Okay, again, this is a finely coated plate, so we don't want to saturate it with a big blob. Even a pipette tip would be too much volume. So what you're going to do is you're going to take a glass capillary spotter, which is open at both ends, and you're going to dip it into your solution, and you're very gently going to release 1 drop of solution onto the plate. Okay. Again, when it's time for acetaminophen, just to be really clear about this, I'm going to change the color of my spotter. You're going to use a new clean spotter, and you're going to spot that into the proper lane for acetaminophen. Okay. Why do we use a clean spotter in between each? I don't want caffeine in my acetaminophen standard lane. I'm trying to learn something about just acetaminophen. If you contaminate your samples, you'll have a hard time distinguishing which spot came from which individual compound as you visualize the plate. Okay. So, once you have your compounds spotted onto your plate, it's time to place the plate into the chamber and develop that plate. Allow it to undergo the process of chromatography. So before placing the plate into the chamber, you're going to want to place your eluting phase or your mobile phase, which is going to be an organic solvent, into the base of the chamber. Okay. You do not want the mobile phase height to be higher than your pencil line. Okay. Your baseline must be above the solvent. When you think about why, we want the solution we spotted to be on the plate. We don't want it to wash away into a sea of mobile phase. So we like to keep the mobile phase below that pencil line. Okay. And what we're going to allow this to do once covered is we're going to allow the mobile phase to travel up the plate. You will actually see the plate get wet. That's how you'll know how far the mobile phase has gone up the plate. Okay. Keeping it covered helps us to keep the environment in the chamber nice and saturated with that solvent vapor, and it allows for a faster developing. We typically stop developing prior to reaching the very top of the plate. So don't let your solvent run all the way up. Okay. We don't want to lose important information. So we want all of our information to be kind of between the baseline and some area below the very top of the plate that we can easily visualize. Okay. So what happens is if you've had different compounds, what we'll find is that they will travel along the plate at various speeds, meaning One might go really fast up to the top of the plate, traveling higher, as shown with the pink spot on the plate. And the other might travel what we call slower, resulting in it traveling to a lower distance, okay? And this is the physical separation we're looking for among different molecules. Why this happens is because in chromatography, each individual molecule will have a different relative affinity for the stationary versus the mobile phase, okay? So what we're going to spend some time taking a look at is where this different affinity arises from. Okay. One of the important concepts in this discussion is going to be polarity. Okay. So we define polarity as an uneven distribution of electron density within a molecule. So you've learned about different polar functional groups, and we'll take a look at how we can use our knowledge of those functional groups to predict something about the way a molecule will behave in a TLC system. So in standard TLC, we're using silica gel as that white powder coating on our plate, okay? Recall that that is our stationary phase. What is silica gel? Silica gel is an inorganic substance, okay? It is not carbon-based. And it typically is thought of as a silicone hydroxide. So what happens is you have a silicone that's highly oxygenated and that has free OH groups along its surface, okay? When we spot with our capillary spotter a solution of our molecule of interest, the molecule adsorbs onto the silica gel surface. Well, what you can imagine from your knowledge of sort of a like dissolves like mentality is that polar molecules will adsorb tighter onto this hydrogen bonding polar surface than a nonpolar molecule might. Okay, so that's our first lesson. This is a very polar surface with lots of hydrogen bonding. A polar molecule will stick or adsorb more tightly. So how does this affect the way that the molecule partitions as the mobile phase starts to travel through? Let's pick a new color for our mobile phase. We'll make it orange, okay? So as the mobile phase travels up the plate, the molecule can desorb off of the surface and travel up with the mobile phase, okay? More polar molecules will desorb less and will thus travel less up the plate than, say, a less polar molecule, okay? More polar molecules will desorb less, okay, as the mobile phase travels. So let me erase my notes here. And let's think about a scenario where we have two molecules, a yellow and a blue, that both adsorb onto the surface. So we have our initial adsorption. As we introduce a mobile phase, we can imagine that the less polar blue molecule will desorb and travel with the mobile phase more than the polar molecule that's kind of stuck on this hydrogen bonding surface. And so what will happen is the blue molecule will travel further up the plate by continually desorbing into the mobile phase and adsorbing back onto the solid phase. We call this a dynamic equilibrium. Neither molecule probably goes completely off of the plate and just rides with the solvent. There is a continuing process of sticking onto the plate, hopping off and traveling with the mobile phase, sticking back onto the plate, hopping off. So the less polar molecule hops off a lot more frequently, and thus it travels farther up the plate. What this ends up looking like is that the blue molecule that's less polar travels higher or faster, and the yellow molecule that's more polar travels slower. And let me make that a little bit clearer in my notes here. More polar. Okay. If you know that, you know everything you need to know about silica gel-based TLC. Okay. So let's take a look at some of the organic solvents that might typically be used as a mobile phase. These will include, though there are many options, I'm going to focus on the most commonly used. 1, 2, 3, 4, 5, 6. Hexane is a hydrocarbon, and it's very nonpolar, as you know from class. Our CH bonds are not our most polar bonds. Okay. Another commonly used solvent that we're going to explore in lab this week is ethyl acetate. And you'll recognize within ethyl acetate this polar ester functionality. Okay, this is a more polar functional group. Okay, so we have an increase in polarity. And one of the other solvents we're going to work with this week in lab is ethanol. And we recognize that this has the polar alcohol group, where we get polarity because more of the electron density is localized onto that oxygen atom. Okay. So what we're going to spend some time looking at in some of the upcoming slides is how the solvent we use has an overall effect on how far the molecules will travel up the plate. And understanding the identity and relative polarity of these solvents is important for that discussion. For this lab, this term, understanding the relative polarity of these 3 solvents among the many you could use for TLC is what I'm going to ask of you. Okay, so let's look at some specifics and consider some different examples using actual organic molecules. Okay. So what we're going to look at first is a scenario like the one we drew out where we have a yellow molecule and a blue molecule. But this time, let's actually associate structures with those. So let's say I have molecule A, which is shown here, and molecule B, which is shown next to it. Ask yourself, which one is more polar? Okay. And hopefully you've recognized that A is going to be our blue, less polar molecule. Okay, so that's going to be in the A lane. And B will make red. That's our more polar molecule. Okay, so when we initially spot these on our plate, both molecules are adsorbed onto the baseline. Okay, so they're both sitting on that silica gel polar surface, and they're held there by some sort of attractive force. Okay. As usual, we're going to place the plate within the developing chamber. And we're going to allow our mobile phase to travel up the plate. Okay. And we're going to go up all the way to, again, what we call our solvent front. Okay. Remember, we always stop that before the very top of the plate. So when we think about which molecule will travel more with the mobile phase, meaning it more easily desorbs from the very polar surface, which one do you think will go higher? You're correct if you've decided that molecule A should travel further than molecule B because it's less polar. And we said in the previous slide that the less polar molecule will adsorb less tightly to the polar silica gel surface. So after development, the blue molecule travels higher. Why? Because it's less polar. Okay. So this is an example of what we talked about on the previous slide, but now you can actually use your knowledge of functional groups to predict that traveling order for specific organic molecules. When we think about how far those molecules travel up the plate, it's fine to say higher and lower, but we like to associate a value with how high the molecules have traveled. So the value associated with how high a molecule travels is known as an RF. Okay. Some people will say RF stands for retention factor. How tightly was it retained on the stationary phase? When I actually learned organic chemistry, someone gave me a little trick too. They said, you could think of it as the ratio to the front, meaning how far does your molecule travel relative to the distance the solvent traveled from your original line to the solvent front. So you can think of this as either a retention factor or a ratio to the solvent front. Okay. However you remember it is okay by me. So when we look at a TLC plate, they're actually quite small. So it's not like very easy to use whole number inches to differentiate the distance that two compounds might have traveled. And we hate to get into kind of tiny, tiny discrete numbers and have to measure, you know, from the line to the spot and just report that. So what we do to make the comparison between how far molecules have traveled a little easier is we first measure the distance from your original pencil line to that solvent front. So that tells us from the baseline to the solvent traveling distance, how far was that? And that's value A, okay? Then what we do is we separately measure how far from the baseline to where my compound traveled. And that distance is B, okay? So what we're gonna do is we'll take the ratio of value B over value A, okay? Because of the way we calculate this, the maximum value is 1 and the minimum value is 0. The closer to 1, the higher the compound has traveled. Okay. Great. So that is RF. So we're going to refer to RF in the next couple of slides as we consider some of the other variable parameters in TLC. One of the parameters that could vary is the mobile phase that you put into your beaker. Okay. We talked about hexanes and ethyl acetate and ethanol. We can use mixtures of those solvents, or we could use pure variations of each of them. So let's come back to our two compounds A and B that we looked at earlier, where we said again that A was the less polar and B was the more polar. And what we decided on the previous slide was that the less polar A would of course travel further or with a higher RF than the more polar B. Okay, so we would expect something like this. Let's say the solvent we were using was a 50-50 mixture of hexanes and ethyl acetate. Okay, 50%, 50%. One is a very nonpolar solvent. The other one is fairly polar. Okay. And so we have a sort of mediocre polarity for our mobile phase. Let's say I take the same two compounds and I develop them in a new TLC chamber. But this time I switch my mobile phase to 100% ethyl acetate. Okay, so this is my new mobile phase. 100%. What you need to ask yourself is, has the mobile phase become more polar? Yes. More polar relative to my starting mobile phase. Then the question becomes, well, what is the effect on what I observe after developing my plate? What you can expect to see with a more polar mobile phase, overall has what we call greater eluting power, meaning it facilitates more desorption of the compounds from the polar surface and allows them to travel more with the mobile phase. Okay, so greater desorption from the stationary phase. What still remains true, even though something has changed, is that desorption is still going to be greater and the RF is still going to be higher for the less polar compound. So what you will observe as the polarity increases is that the RF of every compound goes up, but the relative RF between two molecules remains constant. So you might see something like this, where now A is really bordering the solvent front, and B has jumped up substantially from where it was in our 50-50 mixture. And we'll practice some of these as part of the post-lab questions. Okay, so to recap, take-home messages on these polarity concepts. Silica gel is really polar. As we use an eluting solvent, when that solvent increases in polarity, its power to pull the molecules up the plate increases, and an RF will increase relative to when the plate is developed with a less polar solvent. When spotting two compounds, no matter what the solvent, if you're using a silica gel stationary phase, the less polar compound travels higher, preferentially choosing the solvent. The more polar compound stays lower. Okay, so last little tidbits and logistics. How are we going to visualize these plates? I've drawn pretty colored dots, red and blue and yellow. What if all of our compounds are colorless? How do we see them travel along the plate? What we do to facilitate this, because most molecules we care about do not in fact have color, is we buy a plate with a fluorescent coating. And when we remove the plate from the chamber, we use a UV lamp that irradiates light of 254 nanometers. Okay, so this is what we call UV wavelength light. And what happens is the fluorescent coating on the plate shows up as kind of a neon green, okay? So the fluorescent coating gives off a neon green light. However, anywhere that our organic molecule is, the molecule itself will instead absorb the light and block the fluorescent coating from showing green. So we'll see what kind of looks like a blackish red spot where the light is absorbed. And that's how we know we have our UV absorbing organic molecule. Something that you'll learn more about in Chem 212 probably is that the type of molecules that absorb light in this way, organic molecules that absorb UV light, are typically ones that have multiple pi bonds, such as molecules that contain a benzene ring. Okay, we call those conjugated pi systems. And if you look at the structure of acetaminophen and caffeine as you prepare for lab 1, you will find those grouped pi bonds in this conjugated system. Okay, so that concludes the theory of chromatography and all of the ways that it applies to TLC. Remember to use a clean spotter for each sample and to handle your plate at the edges with clean gloves. In Module 2, we'll take a look at how to separate molecules using what's known as column chromatography. It's a larger version of the TLC plate, and that will include all of the other logistics for Lab 1.